next industrial revolution. So we look at if we look at the past four industrial revolutions, the first industrial revolution is widely taken to be a shift from our reliance on animal and human effort and biomass as the primary sources of energy to the use of fossil fuels and mechanical power this enabled. The second industrial revolution, it saw rapid advancements in the form of electricity distribution, new forms of power generation, and wired and wireless communication technologies. The third industrial revolution saw advancements in electronics, information technology, and automated production. The fourth industrial revolution, let me share my screen again. I think connection dropped. The fourth industrial revolution is being described as the advent of cyber physical systems, which will involve new capabilities for humans and machines. And while these new capabilities rely on technologies and infrastructure of the third industrial revolution, the fourth industrial revolution will bring about new ways in which these technologies become embedded in our societies and even in our human bodies. So, technologies like blockchain, Internet of Things, and big data analytics will play a central role in the cyber physical systems in the fourth industrial revolution. So there is a shift from a centralized web or Web 2.0 towards a decentralized web, which is being called as Web 3.0. And the goal of this next generation web is to enable secure, transparent, and efficient business and financial transactions between a large number of diverse and untrusting entities. So to understand blockchain, we need to look at the history of the internet. So let us go back to the early 90s, where the first generation of the World Wide Web, it was primarily based on the technology of HTTP, which worked to store documents on a computer or a server and made them accessible over internet. And HTML was used to display these documents, and any computer which is connected through a browser, it could access a web page and read the content. So Web 1.0 was primarily static in nature, and content creators were very few, and a vast majority of users were consumers of content. Then by the early 2000s, with advancements in server-side scripting technologies like ASP, PHP, and other technologies, these technologies enable developers to write information to a database and present information, the most recent and up-to-date information in a web page. So the web became more and more dynamic in nature. And Web 2.0 came to be known as the read write web, as it enabled users to interact, collaborate, and become creators of content. So Web 2.0 has given us social media, blogging, video sharing, e-commerce, and all the other large platforms where we spend most of our time today on the internet. And as Web 2.0 evolved, it became more and more centralized with large platforms running out of large data centers, which are under control of large organizations. And with this, the issues regarding security, privacy, and concentration of power in the hands of large enterprises have come forward. And it's only today that we started to discuss about these issues of security, privacy, and centralization of power. And the Web 3.0 is going to bring a paradigm technological shift in this the way the web is going to be structured. So Web 2.0 is more centralized in nature, and Web 3.0 is going to be decentralized. So although the idea of this decentralized web or Web 3.0 has been there around for some while, but only with the recent advancements in blockchain technology, it has actually started to become something real. And the new technologies of blockchain, decentralized storage, and these distributed messaging frameworks and platforms, they will enable us to reconfigure the internet from large centralized servers to fully decentralized nodes. And blockchain is going to play a central role in this next generation decentralized web, along with other technologies like Internet of Things and big data analytics. So let's get started with blockchain. As you already know, what is blockchain? It's a distributed data structure. It comprises a sequence of blocks, and it acts like a distributed database or a global ledger, and it maintains a record of all the transactions on the blockchain network. And these transactions are time stamped and bundled into blocks, where each block is identified by a cryptographic hash. And then these blocks form a linear sequence, which is called a blockchain structure. So this is a visualization of the Ethereum blockchain structure. In this, we can see we have a number of blocks, and each block has multiple transactions. And then on the bottom left, we can see all the transactions which are being broadcasted to the network, but they haven't been processed or mined yet. So the miners or the validators on the network, they process and validate transactions, which are then bundled into blocks, and each block is added to the chain, and then the chain keeps on growing, and the structure itself is called the blockchain structure. So blockchain comprises a sequence of blocks where block is identified by its cryptographic hash, and it references the hash of its previous block or the parent block. And these hash is used to verify that this block is valid or not, and a sufficient amount of work has been done to generate this block. So each block is basically maintaining a record of all the transactions which are received on the network since the creation of its previous block. So instead of storing all the transactions within the block itself, we use a special data structure called a Merkle tree. Because if we store all the transactions within the block, it will become very bulky in nature. And as the blockchain structure grows, the whole blockchain will become very bulky in nature. So instead of storing the entire transactions, we store only the root hash of the Merkle tree. So what is a Merkle tree? It is a special data structure in which we store the data items in the leaf nodes, and then we compute the hashes of these leaf nodes all the way up till the root node, and we store only the root hash within the block. So this is an example of a Merkle tree structure where we have the leaf nodes which are storing the data items, and let's say we store the transaction hashes within the block, and then we compute the hashes of the leaf nodes all the way up till the root node, and then we get the root hash which is stored in the block. So how do hashes help in protecting the integrity of data? So let's say if some hacker tries to modify a certain leaf node, he replaces the data item in a leaf node, that will result in the hashes being changed, and the change in hash will propagate all the way up till the root node. So that results in a different root hash, and that hash is not part of the block within the canonical chain. So that way we can protect the integrity of data. So any transaction cannot be changed once it has been added to the blockchain. So that makes blockchain structure immutable in nature. So once you process and mine the transactions and validate the transaction and bundle those transactions into a block, there is no way to go back in history and change those transactions. So there has been an evolution of blockchain technology over last decade or so, and the current technology of blockchain, it was basically introduced by a person, fictitious person named Satoshi Nakamoto, who's the founder of Bitcoin. In this paper titled "Bitcoin: A Peer-to-Peer Electronic Cash System." And in this, Nakamoto proposed that if you want to build a peer-to-peer version of an electronic cash system which allowed online payments to be sent from one party to another without the need for a trusted central authority or a financial institution. So, what are the ways in which we can establish such a peer-to-peer electronic cash system? So, since there is no centralized authority or a financial institution present, that can lead to the problem of double spending. So double spending can occur when a party manages to spend the same money more than once. So if a user has, let's say, 10 bitcoins in his account and there is no way to secure the network from double spending, then the same user can send those 10 bitcoins to user A and user B. Because there is no centralized authority or a ledger, centralized ledger, then it's difficult to prevent double spending. So Satoshi Nakamoto, he proposed a solution. So he suggested that in order to prevent double spending, firstly we should publicly announce all the transactions, and then we should have a way for all the participants on the network to agree on the transactions and their sequence. So these two key requirements, they led to the development of blockchain technology. So the first version of blockchain networks was the Bitcoin network introduced by Satoshi Nakamoto, and the primary application of this first generation blockchain network was the electronic cash system or cryptocurrency called Bitcoin. Then in around 2013, Mr. Vitalik Buterin, he proposed the idea of a second generation blockchain network, which is programmable in nature. So he proposed that instead of having separate blockchain networks for different types of cryptocurrencies or different types of applications, why not just create a single programmable blockchain network in which we can develop different types of applications, and each application takes the form of a smart contract. So smart contract is nothing but a piece of code which resides on a blockchain and it is given an address, and that makes the blockchain programmable in nature. So Ethereum is the second generation blockchain network. It is a programmable blockchain network, and you can program and develop various applications on Ethereum using smart contracts, and decentralized applications can be developed. So if you look at the development timeline, currently we are seeing blockchain technology entering mainstream adoption, and a lot of applications of blockchain in various other domains like Internet of Things, industry, energy sector, healthcare, financial, and other areas are being prototyped and being deployed. So now this is a visualization of the Bitcoin network and the nodes on the Bitcoin network. So if you see that this is a completely decentralized network, and we have nodes from all across the world, and United States and China have a large majority of these nodes, which are basically miners on the network, which are processing and validating transactions on the network. Similarly, for Ethereum, we have thousands of nodes across the world. Now, coming to the characteristics of blockchain. So, we discussed blockchain is an immutable structure. It's a durable data structure. It maintains records of all the transactions, which are bundled into blocks. And once a transaction has been recorded, it cannot be deleted or altered because we are using cryptographic hashes and Merkle tree structure to store the transactions and the hashes of the transactions within the blocks. It is secure and transparent in nature, and each node is keeping all the copy of transactions which are bundled into blocks. And there is a consensus mechanism within a blockchain network using which the nodes agree on the same block to contain the canonical transactions, and that block is then added to the blockchain structure. So although all the miners are generating their own versions of blocks after each mining round, only one of the blocks gets selected to be added to the chain. There is no centralized authority in a blockchain network. It's a truly peer-to-peer network. And the absence of a centralized authority, it can result in lowering the transaction charges and also ensure faster settlement times. The privacy of transactions is preserved. Each user is given a public private key pair, and the account address of the user is derived from the public key. The private key is encrypted and with the password. And for sending the transactions on the network, we require the private key. So the real identity of the person behind a public private key pair is not revealed on the blockchain network. So that ensures the privacy of the users transacting on the blockchain network. although we are making all the transactions public, but we don't know who are the real people behind those transactions. It is also scalable and available in nature because as more and more peers join the network it becomes more available. So we have two types of accounts in a second generation programmable blockchain network like Ethereum. Uh, we have externally owned accounts and contract accounts. So externally owned accounts are the accounts which are owned and controlled by users. And each externally owned account has an account address, the public private key pair associated with the account, and a balance which is specific to the blockchain. For example, in case of Ethereum, we have the Ether cryptocurrency, which is the native cryptocurrency in the Ethereum network. So each externally owned account has an Ether balance. Then we have contract accounts, which are the smart contracts deployed by users through their externally owned accounts. And each contract account has a contract address, it has a contract code, and a balance. So once a contract is deployed on a blockchain network, it is assigned a unique address, and the code resides on the blockchain network. And once deployed, you cannot alter the smart contract. So it's immutable in nature. You cannot change the smart contract. So what is a smart contract? It is basically a piece of code that resides on a blockchain, identified by a unique address, and it contains a set of executable functions and state variables. And these functions are executed when you send transactions to these functions. So we look at some examples of smart contracts. So let's say we want to set up an escrow smart contract where we want the let's say we have a buyer and a seller, and seller is shipping certain items to the buyer, but the buyer wants to pay the seller only once he receives the item and he is satisfied with the item. On the other hand, we also want to protect the seller so that seller should receive the payment once it has been the item has been successfully delivered. So buyer and seller can come together and they can set up an escrow contract and they can deploy a contract on the blockchain network, and they can program all the conditions and terms and conditions within the smart contract. So the escrow smart contract, it will have a number of variables like the address of the buyer, the seller, the time to expiry, and other variables, and a number of functions which modify the state of the contract. So let us look at how this escrow contract can be used. For example, now we have once we have the escrow contract, the buyer sets up the escrow contract and he makes a deposit to the contract, and this deposit is held within the contract account itself. So as I discussed that the contract accounts on Ethereum network, they have their own balance. So buyer pays the deposit to the contract account, and the balance is held within the smart contract itself. It is not released to the seller. So at the next step, the seller ships the item to the buyer and updates this shipment information. And once the buyer receives the item, he releases 20% of the escrow deposit to the seller. And if the buyer is satisfied with the item, then buyer releases the entire balance deposit to the seller. Whereas if the buyer is not satisfied, he can return the item back to the seller. And then a seller can keep 20% as the restocking fee and refund back the rest of the amount to the buyer. So like this, all these terms and conditions of the interactions between the buyer and the seller, they can be programmed in the form of a smart contract and deployed on a blockchain network. So let's look at one more example. We have a crowdfunding smart contract. Let's say a user wants to raise funds from the public for a certain idea or a certain project, and they want to create a crowdfunding contract. They can program this smart contract and deploy it on a blockchain network and share the address of the contract with all the users, all the people or backers who want to contribute to that campaign. And the users send transactions to the contract and they fund the contract, and all the amount which is contributed to the crowdfunding campaign, the balance is held within the contract itself. Now we check whether this crowdfunding contract, or the goal has been reached at the end of the deadline of this campaign. And if the goal is not reached, then the amount is refunded back to all the backers. Whereas if the goal of the crowdfunding campaign is reached, then the amount is transferred to the beneficiary, which is the user who set up the account. So that way we can raise funds from public for certain ideas using this crowdfunding smart contract. Another example is the voting smart contract. Let us say we want to conduct voting on the blockchain network. So how we can do that? We can set up a voting smart contract, and in this smart contract we have a chairperson who sets up the smart contract, and the chairperson assigns voting rights to specific blockchain accounts which belong to the users. So all the valid voters let the chairperson know their blockchain account numbers, and then chairperson adds those blockchain account numbers to the voting contract, and people who are authorized to vote are specified in the contract. Now each voter sends a vote by sending a transaction to the voting contract and selects the proposal. So there may be a number of proposals. So if there is an election within an organization, there may be a number of people who are nominated for the election, then or candidates for the election. Then users can send their proposal that they want to vote for a specific person. They can let their proposal number know, and the transaction can be sent to the voting contract along with the proposal number. So at the end of the voting period, this contract checks which proposal gets the maximum number of votes, and the address is then the results are then announced. So that way we can ensure that each person is sending only one vote, and we can conduct voting in a secure and auditable manner on the blockchain. Then there are other applications like financial derivative instruments can be programmed on the blockchain network. Now, coming to a blockchain stack, currently we discussed the Ethereum blockchain network, which is one part of the blockchain stack. So, Ethereum is basically a decentralized computation platform where we deploy our smart contracts, and these contracts can be used for various types of applications. We program our application logic within the smart contracts and deploy it on the Ethereum network. But there are other building blocks to this blockchain stack. We have a decentralized storage platform which is called Swarm, and a decentralized messaging platform which is called Whisper. So Ethereum, Swarm, and Whisper, these are the three key building blocks of a blockchain stack. And then on top of these three building blocks, we have a number of decentralized applications or dApps. So what is a dApp? dApp is basically it is a user-friendly interface to a smart contract. So dApp has a front end, a back end, and a contract which is deployed on a blockchain network. And dApps provide user-friendly interfaces to smart contracts. And then we have a number of tools and interfaces. For example, compilers for the contract, smart contract languages like Solidity and Serpent and other languages. And blockchain clients, for example, the Get Ethereum client, Parity Ethereum client, and wallet applications like the Mist wallet, the MetaMask wallet, and a number of dApp frameworks which allow us to develop decentralized applications like Truffle, Embark, and other frameworks are there. So we looked at the decentralized computation platform, which is Ethereum. In this case, Ethereum is an open and programmable blockchain platform, and each node on the Ethereum network, it runs a sandbox environment, which is the Ethereum virtual machine, in which all the execution of the contracts happen, and all the nodes on the blockchain network, they perform basically the same computations, and they provide a redundancy in terms of the execution of the smart contracts. So every time a transaction is broadcasted to the network for a specific contract, it is executed within the Ethereum virtual machine on every node on the network. Then we discussed externally owned accounts. We discussed contract accounts. We looked at blocks which contain the transactions. We looked at transactions. Transactions basically are sent to a specific address. Transactions can be of two types. It can be transactions to transfer value from one account to another. So let's say a user wants to transfer a certain balance from his account to another user's account, from one externally owned account to another externally owned account. That can be one type of transaction. Or we have transactions to contract accounts, where we send transaction to a smart contract and specify the function to which the transaction should be sent, and pass certain variables or input values to the function. Then we have mining, which is the process of validating and verifying the transactions and generating new blocks. We looked at Ether, which is the cryptocurrency, native cryptocurrency for the Ethereum blockchain network. And there is another concept of gas. So, what is gas? So, gas is the native crypto fuel which is consumed when you send transactions to the network. So, every operation that happens on the blockchain network, the Ethereum network, it consumes certain amount of gas. The concept of gas, it's required because we want the miners to be compensated for providing their computational resources, and each miner who mines a block gets a mining reward in the form of certain units of ether. So everyone who sends a transaction to the Ethereum network has to pay a certain amount of transaction fee, which is called the gas fee. And the gas fee, along with the gas fee, we have a price which is set to the gas. So gas price keeps on varying depending upon how much load is on there on the network. So if there is a lot of load on the network, large number of transactions are being broadcasted, then you have to send a transaction with a higher price of the gas, so that it is taken up by the miners. So if you send a transaction with a lower gas price or a lower amount of gas value, then it may not be accepted by the miners and the transaction may get dropped. Another important building block of the blockchain network is the Swarm decentralized storage network, so which allows us to store large files which are chunked and stored on this Swarm decentralized storage network. So blockchain structure, as I discussed, it's not suitable for storing large amounts of data. We are only storing the root hash of the Merkle tree, which of the tree which stores the transaction hashes. We only store the root hash. And let's say we want to store some large data items or large data blobs along with the smart contracts. So instead of storing the data items within the blockchain structure itself, we can use a decentralized storage platform like Swarm, or there is another platform called the IPFS, which is the Interplanetary File System. It's a decentralized peer-to-peer file system, just like we have the BitTorrent system, where each node is storing a certain copy or a certain chunk of the data. And we store the large items on the decentralized storage platform, and then we store only the hash of the data item within the smart contract. Similarly, we have a decentralized messaging platform, which is the Whisper platform, which allows dApps to communicate with each other. Now, if we compare a web application to a decentralized application, typically in a web application, you have a presentation layer which is implemented in HTML, CSS, or JavaScript. Then we have an interaction or communication layer from the front end to the back end, which happens over HTTP or HTTPS. The backend logic is typically implemented using the frameworks or models like Model View Controller, and then we have the business logic running on an application server, and the data is stored in a database, and the static files are stored in a static storage like a cloud storage. So that's a typical multi-tier three-tier stack for web application. We have the application layer, database layer, storage layer, and the front end, the back end communication happens over HTTP or HTTPS. Whereas in case of a decentralized application, we have the presentation layer or the front end, which is again implemented in HTML, CSS, or JavaScript. But the interaction then happens over the Whisper communication protocol. And then the application logic is in the form of a smart contract. And the smart contract is deployed on the blockchain network. And along with the contract, we have a certain JavaScript code which allows the users to interact with the smart contract. The data itself is residing on the blockchain, and static storage. For static storage, we use Swarm or IPFS frameworks or platforms. So that is the difference between web app and a decentralized application. Let's look at the process of setting up a decentralized application on a blockchain network. So we have a decentralized application. Let's say we want to create a decentralized application for a crowdfunding campaign. So we looked at the smart contract example, but that's not very user friendly. If you want backers or public to contribute to the crowdfunding campaign, one way is to share the address of the contract and have those backers instantiate the contract within their blockchain wallets using the contract's address and the interface, and then send transactions to the contract. But that's not very user friendly. So instead, we can use decentralized applications which provide a user friendly interface through HTML or JavaScript, CSS based interface is provided. A web based interface is provided, and from this web based interface, users can interact with the smart contract. So, how do we set up a decentralized application? Firstly, we have a smart contract linked to the decentralized application. So, let's say we have crowdfunding campaign, crowdfunding application. We deploy the crowdfunding smart contract on the blockchain network through an Ethereum node. So, firstly, we compile the smart contract using the smart contracts language compiler, which is Solidity in case of Ethereum. So all smart contracts on Ethereum are implemented using Solidity programming language, which is very similar to the JavaScript language. And then we deploy the smart contract. It is assigned an address, and then that address and the interface of the contract are used within the decentralized application. And then we use this decentralized application to send multiple transactions to the contract. So let's look at an example of the crowdfunding decentralized application. So here we have this application. We have a web-based interface. So in this, we can see that we get information about the address of the contract, how many people have contributed to the campaign, the total funds which have been raised, and the deadline of the campaign. And users can send their contributions to a particular campaign through this decentralized application. So I'm accessing this decentralized application using the Ethereum's Mist browser. So this Mist browser allows you to connect your Ethereum wallet to a particular decentralized application. So you can browse to the address of the decentralized application using this Mist browser and connect your wallet to this decentralized application, and then it'll show you how much funds are there in your wallet, and then you can specify a certain value and send a transaction to the decentralized application and contribute to that campaign. So that is much more user friendly way instead of sending a transaction to the contract directly itself. There is another way to interact with the decentralized application. We can use the MetaMask Chrome extension, and you can browse to the address of the decentralized application. So decentralized application is deployed just like a web application. It can be deployed on any server. It's basically just HTML, JavaScript, CSS files. It can be a static application. So you do not need you can host it on a static cloud storage or cloud hosting as well. and you access the address of the application in Chrome browser and use the MetaMask Chrome extension. So what this Chrome extension allows us, it allows you to connect your wallet, which is specific to the network. So within MetaMask, you can choose which network this application is deployed on. So let's say I've deployed the application on the Ethereum network. I can choose the network and choose my account, and then it will show me my account balance. And this MetaMask extension will connect your account to the app which you are accessing within the browser. And then when you send a transaction, it will ask you to confirm the transaction, and you can then send the transaction to the decentralized application. So that's a very secure way of interacting with the decentralized application from the Chrome browser itself. And the same works even from the mobile devices. So we have a MetaMask mobile application now. And from the MetaMask mobile application, you can browse to the address of the decentralized application and send transactions to the dApp. Now, coming to certain like the applications of blockchain, examples of applications of blockchain in various domains. So we have applications for fintech, financial technology applications are there. For example, banks are using blockchain technology to make the transactions more faster, cheaper, and secure and transparent. Insurance companies can use blockchain technology and set up contracts on the blockchain network. It can reduce it can actually simplify the payment of premiums and reduce the claim frauds. Then we have applications for peer-to-peer lending and crowdfunding. So we looked at the crowdfunding decentralized application. There are a number of applications of blockchain for records and identities. For example, document verification. Let's say you have a certain document and you want to prove the ownership and existence of a document at a certain date and time. Then you can compute a cryptographic hash of the document and store the hash on the blockchain. And then later on, you can go prove that using the same hash, you can prove that this document existed at a certain point in time, and it is a valid document. It's the same document that is whose hash is stored on the blockchain. So proof of existence type of applications can be developed using blockchain and smart contracts. Then marriage certificates, birth certificates, automobile records, land registry records, all these types of applications can be developed on the blockchain and using smart contracts. You can protect your original content, for example, photographs, music, video, documents, and prove the ownership of your content and protect your copyrights using blockchain technology. Basically, you can compute a cryptographic hash of your original content. Let's say there is a script writer, and there are a number of cases of plagiarism in case of movies. Script writers come up and say that okay, this was my script, and this movie director has stolen my script. So one way they can protect their original scripts or original content is that they can write the script in, let's say, a MS Word document and compute a cryptographic hash of the MS Word document and store that hash within a transaction in a blockchain network or in a specific smart contract. They can store this hash value. Now, at a later date, if there is a copyright issue or copyright claim is there and someone steals the same script, the owner of the original content can take the same document which he used to compute the cryptographic hash and recompute the hash again and prove that okay, this was the same document I had 10 years ago, and this was my original script. So that way they can protect the copyright of their original content using blockchain technology. Then we have applications in healthcare like master patient index, electronic healthcare records, patient provider directories, medical insurance claims can be processed on the blockchain, and we can minimize claim frauds. So there are multiple applications of blockchain in various domains. Now, moving on to an important aspect of blockchain networks, which is the mining. So, as I discussed, what is mining? It is the process of generating new blocks on a blockchain network. And every time, like when users send transactions on a blockchain network, either to smart contracts or to other externally owned accounts, these transactions are processed by the miners on the network, and the miners validate the transactions, and then they reach a consensus on a block which should be added next to the blockchain, and the newly mined block is then broadcast to the entire chain. So what the miners have to do, they have a consensus mechanism, and we have multiple different consensus approaches are there. For example, proof of work is one of the consensus mechanisms on the Ethereum blockchain network, in by which miners can agree on the transactions which should be added to a block and which block is valid to be added to the chain next. So proof of work consensus is the algorithm used by Bitcoin and Ethereum blockchain networks. So Ethereum uses a specific version of proof of work algorithm which is called ETH hash. So, and this algorithm, it has been designed to be ASIC resistant. So the issue with the Bitcoin network was that their proof of work algorithm was not ASIC resistant. So what happened? In case of Bitcoin, large mining farms were set up in countries like China. Large factories were set up who were mining transactions on the Bitcoin network, and they gained a large part of the power of the network. So when a network becomes like more and more centralized, because large miners are mining on the network, and the small miners, they do not get a chance to mine on the network because their newly mined block will never be selected because they have less computational power, and large mining firms are being generating new blocks. That leads to more and more centralization of the network, and they were using specialized chips or application specific ICs, ASICs, to speed up the mining process. So that eliminated small miners on the network, and Bitcoin network became more and more centralized in nature. So there were like few large mining groups or mining pools on the Bitcoin network who own or who influence the process of mining and generating new blocks. So in case of Ethereum, the proof of work algorithm has been designed to be ASIC resistant. So this is an example of a block structure, the head block header. Block header, basically it stores a number of fields like the hash to its previous block, the timestamp of the block, the amount of gas used within the block, which is like the gas consumed by all the transactions which are bundled in the block. So as I mentioned, the gas is the crypto fuel which is used within Ethereum, and every user who sends a transaction to Ethereum network has to pay a certain amount of gas. And gas has while sending a transaction, you have to specify a gas value and a gas price. So we store the gas used, and also there is a limit on the number total amount of gas that can be used within a certain block. So we cannot have like an infinite number of transactions within a single block. There is a certain limit on the number of transactions which can be bundled within a block. And then we have like the root hashes. There are three data structures. We have a state root, receipts root, and the transaction list root. So we have three Merkle tree structures within the Ethereum. So we the state information is stored within one Merkle tree, and we store the root hash of the Merkle tree as the state root field within each block. Then all the receipts of the transactions, when a transaction is processed and validated, we get a transaction receipt. So we store the receipt root hash of the Merkle tree, which stores the transaction receipts on the block header. Similarly, bits of transactions are stored in one Merkle tree, and we store the root hash of that Merkle tree within the block header. And also we have a difficulty value, which is there for each block, and the proof of work algorithm requires this difficulty value, and this difficulty value keeps on increasing in each successive block. So these are the number of fields in the Ethereum blockator. I won't go into these details. Let's briefly look at the steps involved in transaction validation. Can you hear some noise in the background if we can? I will request the coordinator to mute all the participants. Okay, let's look at the steps involved in transaction validation. So, firstly, when a miner is validating the transactions and generating a new block, for every transaction, the miner checks if the transaction signature is valid. When you send a transaction on a blockchain network, you have to sign the transaction with your private key, and the signature should be valid. So the miner checks if the transaction has been signed, and if the sender of the transaction is valid, the signature is valid. Then each transaction has a nonce field which is attached to it. The nonce field basically so when a sender is sending multiple transactions, there is a sequence number which is attached to each transaction. So if the miner checks if the transaction nonce matches the nonce of the sender's account. Next, we check that if the gas limit for the transaction is greater than the intrinsic gas used by the transaction. So what that means? Let's say we are sending a transaction to a smart contract. Let's say we are sending a transaction to a smart contract, and the transaction consumes a certain amount of gas. For example, you're contributing funds to a crowdfunding campaign, and the function which is executed within the smart contract, it is consuming a certain amount of gas. So you have to provide a certain gas value along with the transaction. So if your function is consuming, let's say, 1000 gas for all the operations which are calculations which are done within the contract, and you send only 500 gas along with the transaction, then your transaction will be dropped, because the intrinsic gas used by the transaction is higher than the gas limit which you have provided. So you have to specify a gas limit which is higher than the intrinsic gas used by the transaction, and the balance amount is then refunded. So you can specify, let's say, 1500 gas while sending a transaction, and if your contract only uses 1000 gas, you will get the remainder back to your account. So you should always pay a higher transaction fee than would actually be used by your transaction, so that the balance then can be refunded to you and the transaction is successfully mined. Next, we check if the sender account balance contains at least the total cost required to pay for the upfront payment for the transaction. So if you are sending certain gas, you are specifying certain gas limit, you should actually have that much balance in your account. And finally, we check whether the block's gas limit has not exceeded. So each block has we specify a certain gas limit for the blocks, and we can only include a limited number of transactions within the block. So if the gas limit of the all like the total gas used by all transactions within the block has not been exceeded, then that transaction is processed. So for every transactions, we follow these 6 steps. Each miner processes every transaction and generates his own block after each mining round. And then their own blocks are broadcast to the network, but only one of the miners' block is selected. And then that block is added to the chain. And the miner whose blocks get selected to be added to the chain gets compensated in the form of a mining reward. So in every block, there is a transition in state. So basically, we are storing the ledger or the state information within a blockchain, or each block is storing a certain state information. So that is, let's say we have the balances on each and every account on the blockchain network is stored as the within a state drive, or a state Merkle tree structure is used to store the state information. Now, when we send transaction from one account to the other, or from one account to a contract account, the state has to transition from the current state to the next state. So if I'm transferring a certain value from my account to another user's account, when a transaction is processed, there should be a state transition. So what is the process of state transition? So in this flowchart, we can see first we calculate the total fee for the transaction and subtract the fee from the sender's account. So the sender who is sending the transaction to the blockchain network, the transaction fee is deducted from his account. Next, we check the type of the transaction. So as I mentioned, there are two types of transactions. They can either be to transfer value from one account to another, or they can be to send a transaction to a contract. We have contract transactions or account to account transactions. So if the transaction is to transfer value, then you transfer the transaction value from the sender's account to the receiver's account and check the status of the transaction. If the transaction has succeeded, then send the cost of the gas used to the block's Coinbase account, or the account who is mining the block, and refund the cost of the remaining gas back to the sender. So the remaining transaction fee is refunded back to the sender, and the gas used for the transaction is given to the miner of the block. And then we update the block's state tree, which is the Merkle tree. We update the Merkle tree, which is storing the state information, and compute a new hash for that Merkle tree and store the root hash within the block. Similarly, if the transaction was to a specific contract, then we execute the contract code, and if we check whether the contract execution has succeeded or failed, and follow the same process. Similarly, we have steps involved in block validation. We check whether the block's previous hash is valid, and the block's previous hash and the parent's hash match each other. So as each block is pointing to its previous block, so the block's previous hash field within the block's header should be same as the parent's hash. Then we check whether the block's number is a successor of its parent's block. So each block has a number. It should be a successor to its parent's block number. And then there are a number of other steps. Let us not go into each and every step. We can skip these details. Now, moving on to like a brief introduction to various types of consensus algorithms. We looked at proof of work consensus, which is used by Bitcoin and Ethereum. Proof of work is a transaction validation and consensus mechanism used in Ethereum and Bitcoin networks. And it is basically a cryptographically secure nonce that proves that a certain amount of work has been done to generate a particular block. And each miner on the network computes a proof of work, a nonce field, which is added to the block. But the issue with proof of work is that it consumes a large amount of energy, because all the miners on the network are basically doing redundant redundant validations. Each miner is generating his or own version of the block, but only one miner's block gets selected. So there is a lot of energy wasted in proof of work blockchain networks. So instead of proof of work, we have a better algorithm, consensus algorithm, which is proof of stake. It is an alternative to proof of work in which we have the nodes on the mining on the blockchain network, which are called validators, and these validators are basically they stake a certain amount in the network in the form of a bond or a security deposit. So if I have to mine or if I have to process transactions on proof of stake network, I have to deposit a security deposit or a bond on the network, and then I'm allowed to process or validate the transactions. And the network randomly selects one validator and assigns it the right to create the next block. So there is no mining as such on the proof of stake networks. Only one of the validators is selected at each mining round. At each round, we select only one validator, and he's allowed to generate the next block. And since he holds a bond or a security deposit in the network, if he processes certain wrong transactions, then his bond or security deposit is forfeited. So that ensures that the validators are uh, validating only the correct transactions. Then we have proof of authority consensus algorithms, in which it is a modified form of proof of stake, where instead of staking a monetary value or a deposit, you stake the identity of the user. So in proof of authority networks, let's say we have a number of organizations which are creating their own private blockchain network, and each organization has a blockchain account, and you make those accounts as authority nodes, or those organizations as authority nodes on the proof of authority network, and you are staking your identity. So if an organization is processing certain wrong transactions, we know who is doing that. So the identity behind those real accounts, the real identity behind those accounts is revealed, and your identity is at stake. So here is an example of consensus algorithms used by various blockchains. We have proof of work in Bitcoin and Ethereum networks. Then we have the Ethereum's Coven testnet, which is using proof of authority. Next generation, third generation networks are using proof of stake or delegated proof of stake and other consensus algorithms. Finally, here is a comparison of various blockchain networks: the first generation Bitcoin, second generation Ethereum, and third generation networks like Neo, Lisk, and EOS. And they use various types of consensus algorithms like proof of work, proof of stake, delegated proof of stake. Ethereum and other networks are programmable in nature, so they allow smart contracts. In Ethereum, we develop smart contracts using Solidity. In Neo, we use Python, C Sharp, Java. Lisk allows smart contracts in JavaScript. EOS allows contracts in C++. Then we have block times, which is the time after which a new block is generated. Bitcoin has a block time of 10 minutes, whereas Ethereum has 12 seconds, and other networks have much smaller block times. So, amount of transactions which can be processed on the first generation network Bitcoin is quite less. So, you can only process 7 transactions per second on Bitcoin, whereas in Ethereum we can process 15 transactions per second. And in third generation networks like EOS, we can process 100,000 transactions per second. They are much more scalable and faster as compared to the earlier networks. And each network has its own native cryptocurrency. In Bitcoin network, we have Bitcoin, Ethereum has Ether, and similarly for other networks, they have a native cryptocurrency which is used. So to summarize, what are the benefits of blockchain? We have blockchain is decentralized and trustless network. So it establishes trust within a set of untrusting entities. We have networks which are blockchain networks are resilient to failures since it is fully decentralized and peer-to-peer in nature. There is no single point of failure. Blockchain networks are scalable as more and more peers join the network. It becomes more scalable. The computing capacity of the network scales up. It is secure and auditable in nature since all transactions are secured by strong cryptography, and we are storing the root hashes of the Merkle trees, and transactions are stored within the Merkle trees. We cannot change the transactions. It is autonomous in nature, it can enable different entities to communicate with each other and do transactions autonomously without the need of a trusted central authority. But there are a number of challenges associated with blockchain. Firstly, there are issues with respect to smart contract vulnerabilities. So, since smart contracts are basically a piece of code which is deployed on a blockchain, and if there is a software vulnerability or a bug in your smart contract, which allows the hacker to exploit the contract, then they can drain all the funds from your contract. And there have been incidents, like in June 2016, one attacker managed to drain more than 3.6 million ether from the smart contract belonging to a decentralized autonomous organization because there was some recursive call bug associated within the smart contract. Then there is lack of awareness right now with respect to blockchain technology, and it's still a nascent technology. It is being mostly adopted in the financial sector right now, but there is still lack of awareness. And also, regulatory issues are there with respect to cryptocurrencies, and that is restricting the widespread adoption of this technology. And issues with respect to privacy and scalability are there. For example, in first generation Bitcoin network, you can only process 7 transactions per second. So scalability is one big issue with blockchain networks right now, and the next generation, third generation networks are trying to address these scalability issues with better consensus mechanisms like delegated proof of stake or proof of authority networks. Consensus algorithms are being used. So for further reading, these are some of my books in the hands-on approach series on cloud, IoT, big data, blockchain, and the recent one is on cloud solutions architect. So if you have any questions, I can take up your questions now.
Hello.
Yeah.
Yeah, sir, good afternoon. Good morning,
Afternoon.
rather. First of all, I would like to thank you.
So I request please unmute who was asking question because I mute all. All of you please unmute one by one. If somebody is asking question, please keep yourself on mute. Yes, sir.
Yes, sir. First of all, I would like to tell every participant that Ashdeep sir is the person who is the main author of the block diagram of the smart contract. And every researcher who is going to research about the blockchain, going to use the smart contract block diagram,
ये हमारा alumni है.
permission from sir. So thank you so much, sir, for such a great lecture. The question I would like to ask is, since we know that proof of work is not good as proof of stake,
patent
Yeah.
we are using proof of work in Ethereum. So what is the reason for that, sir?
Yeah. So the reason is once the network goes live, and there are lots of miners on the network. It's very difficult to bring like major structural changes within the network. So it's easier to start a new network than changing the network after it has been running for a while. So while there are like minor changes or minor upgrades to the Ethereum network, but to bring drastic changes like changing the entire consensus algorithm, that will actually lead to a lot of difficulties. So that's why the next generation networks are using better algorithms right from the beginning.
Okay, sir. Thank you
And
so much. Yeah.
also there has to be a consensus in the community. So what happened with Bitcoin network, like a certain part of community, they wanted the block size or block time to be changed, whereas the other part of community didn't want those changes to be done. So that led to the splitting of the Bitcoin chain. So now we have number of different variants like Bitcoin Gold, Bitcoin Diamond, and other variants are there
So
because the
can we
community
use
wasn't able to reach the content. Yeah.
can we use proof of stake also in Ethereum network?
Yeah, not in the main Ethereum chain, but
Okay.
if you want to start your own chain, and if a group of miners they want to use proof of stake, they can actually start a side chain. Like you can announce that from block number, let's say 100,000 block number onwards, all the transactions are going to use proof of stake. So that will create a separate side chain.
Right.
You will start your own chain. So in case of Ethereum as well, if you see, there are two Ethereum chains. We have Ethereum Classic and Ethereum.
Mhm.
Because at certain point, at certain block, the community didn't agree on whether a contract transaction should be processed, because there was a hack that happened in this DAO account, and 3.6 million ether were stolen.
Okay,
So
sir.
the Ethereum, the main community said that okay, let's not process this transaction which hacked the